Okay guys, we are going to pick up on page 51, starting with section 7.2 in your course notes. And this section starts the topic known as inferential statistics. And we're going to use inferential statistics when we want to estimate a parameter. So suppose we want to know the proportion of voters that are going to vote Democratic this upcoming election. We might sample some voters and have an estimate for that proportion. But what most people do when they have an estimate of this proportion is that they give what's called a margin of error. And the margin of error is what we tack on to our estimate to give us an interval. So we know that our estimate's going to be off a little bit because we're only sampling a small portion of the population. And that's why we give a margin of error. And so this section goes over that. So before we get started, let's give a couple notation symbols. So the letter P is the population proportion. So for our voting example, is the proportion of all voters who will vote Democratic or Republican, whichever you prefer. Okay, and so that's what we're trying to estimate. So we go out and we take a sample and we calculate what's known as p hat. That's the second symbol here. P hat is the sample proportion. And that's calculated when we collect data. Okay, and then Q hat is just 1 minus P hat, and we need that. That's the people that are voting the other way. And so that's the symbols that we're going to use throughout this section. One important note is that we always make our percentages into proportions when we're doing these calculations. And so we use P hat as the sample proportion. That's our estimate of the population proportion. And that estimate is called a point estimate. Okay, so P hat, so the P with the caret over it, that's called P hat, is a point estimate. And what we mean by a point estimate is an estimate of some population parameter. Well, I don't need to say population. Parameter means it's from the population. And so we take a sample as usual, and our sample is an estimate of some parameter, and that so it's called a point estimate. P hat happens to be an unbiased estimate. That means it doesn't systematically over or underestimate the parameter. Alright, so along with our point estimate, we also want to know how confident we are or how good that estimate is, how precise is that estimate. And so what we do is we calculate a margin of error. That margin of error gives us our precision of the estimate. And so we know that P hat's going to be off a little bit, and so that's why we calculate a margin of error. To calculate the margin of error, or a confidence interval is what we're getting at. We need to know how confident we want to be. Do we want to be very confident that we've captured the parameter? Well, yes. The answer is yes. And so the confidence levels that we use are 90%, 95%, or 99%. And so we want to be pretty confident that our estimate plus or minus the margin of error has captured the true parameter. Okay, so I'm going to just jump down here a little bit. So we need to know a critical value that comes from the normal distribution. And if we want to say calculate a 95% confidence interval, we want to get the z-score that represents the middle 95% of the data. And so if I did my little curve here, we would want to capture the middle 95%, Alright. You can just imagine there's a line there. There we go. And so we want the middle area to be 0.95. So the area to the left of, say, this z-score is 0.975. And so we can use our table and look up the z-score for 0.975. So we want the area to the left to be 0.975. We're looking for 0.975 in here, and I can find that exactly. And it turns out the z-score is 1.96, so 1.9, and then that goes up to 0.06. So going back to my notes. So the corresponding z-score is 1.96, and that represents a confidence interval for 95%. So we can get all the confidence critical values from the table, but we don't need to do that because we only have a few that are common. And if we use a 90% confidence level, then the critical value is 1.645. And if we use a 99%, then it's 2.58. Alpha just represents 1 minus the confidence level, so this is 0.1, and this would be 0.01. Okay, so now we're going to go ahead and calculate a confidence interval. An interval means there's a lower bound and an upper bound. A confidence interval is two parts. It's the point estimate, which we know is p hat, plus or minus the margin of error. So our margin of error is this right here. That's the margin of error. And we calculate that by taking one of our values. This depends on the confidence level. And then we put the sample proportion in there and the sample size. And so we get a confidence interval by taking our point estimate, p hat, plus or minus the margin of error. So we get an upper bound and a lower bound. So your lower bound is p hat minus the margin of error, and your upper bound is p hat plus the margin of error. And so that gives us a range where we're confident that the true proportion falls. Okay, so the three requirements for the confidence interval to be valid is you have a simple random sample, from your population. That's SRS, simple random sample. You have a fixed number of trials. That's your sample size n. And let's see, one more. And then your sample size is large enough. So you have at least what we call 5 successes and 5 failures. Success or failure is just a generic term because there's only 2 outcomes. So let's go ahead and try a problem. I'll show you how to do it by hand, and then I'll show you how to do it on the calculator. So an important issue facing Americans is the large number of medical malpractice lawsuits and the expense that they generate. In a study of 1,228 randomly selected lawsuits, so this is your N, it is found that 856 of them were dropped. So this is your what we call X. That's how we're going to calculate p hat. So we want to construct a 99% confidence interval for the proportion of lawsuits that are dropped or dismissed. Okay, so you can go ahead and read part 1. Let's go ahead and jump to part 2. We first want to calculate the sample proportion. So p hat is just the proportion of lawsuits that were dropped. and that's going to be equal to your count or number that were dropped divided by your sample size. It's just the sample proportion that have been dropped. Okay, so there were 856 of them that were dropped, and there were a total of 1,228. And so our p hat's going to be 0.697. All right, and now we want to compute the margin of error for a 99% confidence interval. Okay, so 99%, and we're going to use this formula up here that I circled. So 99% means our z-value is 2.58. That's the value that goes in here. The notation's a little bit confusing, but we just put that value in there. So our margin of error is going to be 2.58 times the square root of p hat, which we just calculated as 0.697. And then we need 1 minus 0.697 for q hat. That's 0.303. That's equal to q hat in our formula. So times 0.303 divided by our sample size. Okay, so that's the margin of error. That's 0.0338. And so our confidence interval, let's go back up here. Our confidence interval is just p hat minus the margin of error and p hat plus the margin of error. Okay, so we have 0.697, and I'm going to use this plus minus notation, 0.0338. That means we take 0.697 minus 0.0338. That gives us 0.6632. And then we take 0.697 plus 0.0338, which is 0.7308. Okay, so there's my confidence interval. And then we'll do it on the calculator as well. Okay, so for the calculator function, we want to go to stat. And then we want to go, everything else we're going to do, we're going to go to tests for pretty much the rest of the semester. We're going to go to tests, and then we want to go all the way down to, I think I just passed it, the one prop z interval. So, oops, passed it again. Letter A. Okay, so one prop z interval. And then I want to enter my value for x. So that was 856. I enter my value for n, which is 1228. My confidence level was 99. And then I just hit calculate and enter. Okay, so here's my lower bound and here's my upper bound, which is pretty much what we just calculated, a little bit of rounding error.